Hello people watching at home. I'm Andrew Flood, a PhD student at the University of Toronto, and I'm going to walk you through a poster I did on using evolutionary algorithms in the optical design of bifacial thin crystalline silicon photovoltaics. This is up at Next Generation Solar, but unfortunately I couldn't be there, so you're getting this walkthrough of a different sort. So before continuing on, it's good to note that this is a collaboration between the Climbing Group at McMaster University and the Chronic Group at the University of Toronto as part of Network Project 10. So in addition to myself, Kevin Boyd has assisted in this work. All right, so what's the point of this work? As part of this collaboration, we're working with 2 micrometer thick crystalline silicon membranes and attempting to fabricate cells on top of them. So you can see an image of a membrane being held up to a light in figure 1. And you can see that's quite thin. We got a lot of light through there. So we'll need to optimize this optical structure to make sure we absorb as much light as possible. So as part of this optimization, we're looking not just when the cell is illuminated from the front, but when it's illuminated from both the front and the rear. This is a bifacial arrangement. It can come up in certain architectural arrangements. So if you have them standing vertically or have a, say, white paint on your roof and the cells are particularly spread out, then bifacial arrangement may be the best way to treat it and to optimize too. Certainly it's getting mentioned a bit more these days. So when you just treat front illumination, you can optimize by scanning through different parameters. Right? So the optimal case is usually having a Bragg stack on the back of very high index contrast layers, and then a very good anti-reflection coating on the front. Once you move to bifacial arrangements, it's less clear what the optimal structure would be. Do you move your rear reflector to lower index materials so that you get more light coming through, you don't get as much reflection, and a narrower band of reflection? Or does it work to shorter stacks, so you do 2 bilayers instead of multiple? Does the front become a stack as well, or does it stay anti-reflection? At what point does this transition as the illumination gets higher on the rear? It's a bit more complicated, and you can't do it by scanning through parameters, particularly when you have a lot of possible materials. So our approach to this problem is to use an evolutionary algorithm. It's exactly what it sounds like. It applies principles of evolution to some population structures, and you hopefully by the end, as you go through natural selection, get a more optimal solution, right? Or the optimal solution, depending on how you do it. Okay. So for us, we start with 60 randomly generated structures. That means 2 micron thick crystalline layer is there for the absorber, but on the front and rear, the layers are randomly generated. Then we perform some breeding, so crossover. So we take 2 of them and we say, hey, you're going to be parents, and then we'll have a child based on what their different layers on the front and rear was, right? There's some chance that they'll get either what their parents had. After breeding, so once we've generated the children, we look at the mutations. So it'll change things like the thickness of a layer, the material of a layer. The layer might change in position, removing a layer, adding a layer. This is handles for each layer. In addition, there's a multi-copy. So that'll copy multiple layers, say 1, 2, or 3, and shift them down. This was important to put in there because we know that some of the best cases already consist of Bragg stacks, particularly when there's no rear illumination. So I wanted to make sure that we could traverse different Bragg stack ideas relatively easily. And lastly, we have the selection of new populations. So those which have the highest generated photocurrent, and it's just optical, so we just worry about the number of photons absorbed. So highest number of photons absorbed, the top 60, they live, the bottom 60, they die. And that top 60 just continues. Right? This way of just keeping the best ones every time does have some issues, and we'll see that in the results. So some modifications will have to be made, but it's a good point to start. So this whole evolutionary process, so the breeding, the mutation, the selection, going through that whole cycle, it's done 100 times. We do about 100 generations. Now you can do much longer, but we do 100 generations for this preliminary study. So in terms of results, looking at our chart in figure 4, it shows how our photocurrent is increasing over different generations. So cycles through that whole evolutionary process. Each of those lines is for a different amount of rear illumination. So 0% is no rear illumination, 100% is equal illumination from both sides, 50% is half the intensity from the rear as from the front. Now, we should expect to have always higher photocurrents for increased rear illumination. I mean, there's more photons to harness in our optimal cases. This is not true between 0% and 10%. If you look at the actual structures that count optimization, you can see why. It's because we have, for the 0% case, it's evolved a 2-layer anti-reflection coating, whereas for the 1-layer case, it just is a 1-layer anti-reflection coating. And the 2-layer is a much better anti-reflection structure. The reason you don't get it is because we have such a strong selection for the best one. So if you end up with like an optimal 1-layer one, it's going to be very difficult for it to, say, mutate to a suboptimal 2-layer one. It just won't happen. And that has to do with our selection process. That's why we have to modify that to ensure that we're always getting the most optimal cases, which currently is not what's happening. So if we take a step back and look at the overall trends in the structure, we find that we go from those very high index different rear reflectors towards lower index rear reflectors, so from crystalline silicon to titanium oxide, and then down to silicon nitride, it goes to lower indexes. And then eventually at about 50%, it starts becoming more just asymmetrical anti-reflection coatings until you get to 100% where it is pretty much symmetrical. You can see it's not exact, but that's because it hasn't been refined. This is evolutionary, so it's a bit random, right? So we need further generations or another optimization routine to sort of build in there. Now, the other important things to note are how there's things in there that I wouldn't have ever come up with, right? So the silicon nitride at x equals 20% of rear, the silicon nitride sort of anti-reflection on the rear of the stack, and same for that intermediate titanium oxide layer on the x equals 40. This wouldn't be anticipated, but it comes out of the algorithm as something that you would want to put in there. So to conclude, we've developed an evolutionary algorithm for the optimization of bifacial silicon cells, at least the optical portion, right? This is all done in 1 dimension, but it can be expanded for multiple dimensions. The principles remain the same. The point here is to explore what's important in the algorithm. So we've seen that the selection process is very key. This is known, so some modifications will be done there to improve the algorithm, but the trends will probably valid. So where we see the change from high index Bragg stacks to lower index Bragg stacks, and also where it switches over to antisymmetric coatings right up to 100% rear illumination, where we get those symmetric case. So I'd like to acknowledge the funding support of NSERC and the Photovoltaic Innovation Network itself. If you'd like to contact me about this work, you can see my email address at andrew.flood@mail.utoronto.ca, and I'm a member of the APD group at the University of Toronto. Thank you.